The SBSA Hypercube as a rotation group, twist operators, Coset projections, and instantaneous address recovery. Formalizing size-based slot allocation through the lens of Rubik group theory. Aaron Cattell. Extended from SBSA Hypercube System Algebraic Foundations, Capacity Bounds, and Complexity Analysis, 2025. Abstract. The size-based slot allocation, SBSA, Hypercube H equals S times T times W times V with H almost equals 1.6 times 1016 addressable locations admits a natural group structure analogous to the Rubik's cube rotation group. We introduce four face twist operators R, U, F, L acting on the four SBSA dimensions, show they generate a finite group SBSA of order 4 equals 24, and prove that any element of H is recoverable by at most one twist sequence of length less than or equal to 3 from any other. The central result is the twist address isomorphism theorem. Each group element of SBSA corresponds to a coset projection onto a dimensional subspace, and the linear address formula of SBSA is precisely the group homomorphic image of this projection. Information retrieval therefore reduces to twist composition, an O1 operation at every level. Section 01 Introduction and Motivation. The SBSA system established in 1, 2 maps each file to a unique 4-tuple S, T, W, V, set membership symbol H via a linear address function, proving O1 insert, lookup, and delete. The algebraic machinery invoked was largely that of arithmetic progressions and quantization operators. A structurally richer question remains: does the hypercube possess symmetries that can be exploited for navigation? The Rubik's cube offers a template. Its 3x3x3 grid of cubies is not merely a combinatorial object. It is the quotient of a group acting on labeled faces. Crucially, the solved state is recoverable from any scrambled state by a finite sequence of face turns. Remarkably, no matter the scramble, 20 moves suffice, God's number 4. We transplant this structure onto SBSA. Each of the four SBSA dimensions, size class S, thickness T, width W, version V, is assigned a twist operator acting as a cyclic permutation of its index. The hypercube becomes a direct product of cyclic groups, and address computation becomes group multiplication followed by projection. The practical payoff is immediate. A distributed system can shard the hypercube along twist orbits, and a query resolved by composing at most 3 twist operators finds its target in constant time regardless of H. Section 02 The Rubik analogy, dimensions as faces. A standard 3x3 Rubik's cube has 6 faces and 6 corresponding generators R, L, U, D, F, B of the Rubik group Rubik, a subgroup of the symmetric group on 48 facelets. The SBSA Hypercube has 4 dimensions. We assign 1 face twist per dimension. R size class SSS1, mod 4. U thickness TTT plus T, mod tmax. F width WWW plus W, mod WM. L version VVV plus 1, mod vmax plus 1. Definition 2.1, twist operator. For each dimension di approximately equal to ni, the associated twist operator I, HH is defined by I x1, xn, equals x1, 11 plus 1i, xn. Where plus denotes addition in ni and 1i is the generator of the ith factor. In Rubik notation, R equals S, U equals T, F equals W, L equals V. The inverse of each twist, written R, U, F, L in standard Rubik notation, simply decrements the corresponding coordinate. I1, x1, xn, equals x1, 11 1i, xn, 2.1. Definition 3.1, SBSA twist group. Group. Let SBSA be the group generated by the four twist operators and their inverses under composition. SBSA equals S, T, W, V less than or equal to sim, H, 3.1. Theorem 3.2, Group Isomorphism. The SBSA twist group decomposes as a direct product of cyclic groups. SBSA approximately equal to 4 times 20001 times 1999981 times 10001, 3.2. And therefore SBSA equals H is equal to 1.599984 times 1016. Proof. Each I acts non-trivially on exactly one coordinate, and as the identity on all others. Consequently Ij equals Ji for all I not equal to J, the generators pairwise commute, so SBSA is abelian. Since INI equals ID and the orbits of each I are the fibers of the projection onto Di, the subgroup generated by I alone is cyclic of order Ni equals Di. The direct product structure follows from the independence of coordinates. This stands in deliberate contrast to the Rubik group Rubik, which is non-abelian of order 43 quintillion 252 quadrillion 3 trillion 274 billion 489,856,000 almost equals 4.3 times 1019. The SBSA twist group is abelian because its dimensions are independent. There is no QB sitting at the intersection of two faces that must be moved when either face turns. This independence is precisely what guarantees O1 lookup. Corollary 3.3. Every address is reachable in one twist sequence. For any 2 points P, Q set membership symbol H, there exists a unique group element G set membership symbol SBSA such that G times P equals Q, explicitly. G equals SS, TT, WWVV, 3.3. Where S equals QSPS, mod NS, and similarly for the other coordinates. The full Cayley graph of SBSA has H almost equals 1.6 times 1016 vertices, unrenderable. We illustrate the structure by projecting onto the smallest two dimensions, S times V, forming the group 4 times 4, taking V mod 4 for clarity. Each directed red edge represents a single R twist, increment in S. Each directed blue edge represents a single L twist, increment in V. The grid topology makes clear that the graph is toroidal, a discrete torus, and that any node is reachable from any other in at most 6 steps along this projection. Projection 0, 0, 1, 0, 2, 0, 3, 0, 0, 1, 1, 1, 2, 1, 3, 1, 0, 2, 1, 2, 2, 2, 3, 2, 0, 3, 1, 3, 2, 3, 3, 3 R twist, size class, L twist aversion, dashed equals wraparound mod n. Figure 1. Cayley graph of 4 times 4, the S times V projection of SBSA. Nodes are labeled S, V. The full 4-dimensional graph is a 4 torus. Section 05 The twist address isomorphism theorem. The linear address function of SBSA, proved bijective in 1, is not merely an implementation convenience. It is the canonical group homomorphism from SBSA to the cyclic group H. Theorem 5.1 Twist address isomorphism. Define the address map phi H by phi S T W V equals S times NTNWNV plus T times NWNV plus W times NV plus V 5.1. Then phi is a group isomorphism SBSA approximately equal to H, and for any twist I. Phi I x equals phi x plus stride mod H 5.2. where the dimensional strides are strides equals NTNWNV stride T equals NWNV stride W equals NV stride V equals 1, 5.3. Proof. Homomorphism. Let G equals I1K1 incomcom. Since each I acts on exactly one coordinate, and coordinates are independent, phi G times X equals phi X plus sigma J Kij times stride A, mod H. This is exactly multiplication by a fixed element in H, confirming phi is a homomorphism. Bijectivity. Proven in Theorem 3.3 of 1, phi admits an explicit inverse via the modular arithmetic chain 1, algorithm 2 of 1. Stride formula. Applying S increments S by 1 and leaves T, W, V unchanged. Thus phi, S, X, phi, X, equals NTNWNV equals strides. The other cases are identical. The theorem says that every twist is a stride addition in address space. A sequence of twists is therefore a sum of strides, still O1. This is the algebraic core of SBSA's performance guarantee, now recast in group theoretic language. Section 06 Information Retrieval as Coset Navigation. Suppose a query arrives specifying only a subset of coordinates, for example, find all files with size class S equals 2 and version V equals 7. In Rubik terms, this is equivalent to fixing two faces and asking which layer positions are consistent. Definition 6.1 Dimensional coset. For a partial specification sigma, I pi set membership symbol I, di over an index, subset I subset symbol of S, T, W, V, the corresponding coset is C equals X set membership symbol H11 equals I for all I set membership symbol IA 6.1. This coset is a subgroup translate in SBSA and corresponds to a contiguous block of addresses in H. Lemma 6.2 Contiguous address block. If I equals S affixing only the size class to S0, then the addresses in C form the contiguous interval. S0 times strides, S0 plus 1, times strides 1, proper subset symbol H, 6.2. The address of the cosets, origin, smallest indices in free dimensions, is exactly S0 times strides, accessible by a single RS0 twist from the identity element. Proof. By Theorem 5.1, fixing S equals S0 and varying T, W, V freely ranges over NTNWNV consecutive integers, beginning at S0 times strides. The retrieval protocol, then, is simply compose the twist operators for the known coordinates, read off the resulting linear address, and jump directly to the target memory location. No search, no comparison chain, a single arithmetic evaluation. Query type. Twist sequence. Complexity. Addresses returned. Full specification, S, T, W, V. RSUT, T, F, W, W underscore minute, WLV. 01. 1. Fix S only. RS. 01. NT times northwest times NV. Fix S, V. RS LV. 01. NT times northwest. Fix T, W. UT, TF, WW underscore minute, W. 01. NS times NV. For the Rubik's Cube, God's number is 20, the maximum number of face turns needed to solve any scramble for. For an abelian group, the analogous quantity is far simpler. Simpler. Theorem 7.1, SBSA God's number equals 4. Every element of SBSA can be expressed as a product of at most 4 twist operators, 1 per dimension. That is, the diameter of the Cayley graph of SBSA with respect to the generating set S, T, W, V, O and their powers is diam key SBSA I equals 4, 7.1. Proof. Since SBSA approximately equal to D1 times D2 times D3 times D4 with generators 1 per factor, any group element G equals G1, G2, G3, G4 is reached by the word 1G1, 2G2, 3G3, 4G4. A product of exactly 4 generators, some possibly at the identity power 0. No element requires more. This theorem has a striking practical interpretation. Any file in a SBSA Hypercube is exactly 4-dimensional moves away from any other file. In an implementation using actual multidimensional memory hardware, this would correspond to 4 pointer dereferences, an irreducible minimum for a 4-dimensional address space. Section 08 Algorithm, Twist-Based Address Recovery. SBSA twist-based lookup input, query Q equals S, T, W, V. None means unrestricted output. List of matching linear addresses function twist underscore lookup, Q, SBSA underscore params NS, NT, Northwest, NV equals SBSA underscore params, dot cardinalities 4, 200,001, 1999981, 10,001 stride equals NT asterisk Northwest asterisk NV, Northwest asterisk NV, NV, 1. Stride vector base underscore address equals 0 free underscore strides equals 4I, 11, psi, NI in enumerate, zip, Q, stride, NS, NT, Northwest, NV if 11 is not none, base underscore address plus equals 11 asterisk psi apply twist caret to X or else. Free underscore strides dot append, psi, NI, dimension remains free enumerate coset, base underscore address plus all combinations over free dims return coset underscore enumerate, base underscore address, free underscore strides, function coset underscore enumerate, base, free underscore strides, free strides define a sublattice, iterate it results equals base 4, stride underscore I, NI, in free underscore strides. Results equals R plus K asterisk stride underscore I for R in results for K in range, NI. Return results, full specification case. Free underscore strides equals exactly 1 address returned. All arithmetic is mod H, but with non-overlapping strides this is automatic. The twist underscore lookup function performs 1 multiply-add per restricted dimension, at most 4 arithmetic operations, independent of H. It is O1 in the lookup step. The enumeration of the coset is OC, but is only needed for range queries, not point lookups. Section 09 Comparison, SBSA group versus Rubik group. Property. Rubik group Rubik. SBSA group SBSA. Order. Almost equals 4.3 times 1019. Almost equals 1.6 times 1016. Abelian. No. Yes. Structure. Complex non-abelian quotient. 4 times 2000001 times 1999981 times 10001. God's number. 20, face turn metric. 4, 1 twist per dimension. Cayley graph topology. Complex, diameter 20. 4-dimensional discrete torus. Address recovery. Non-trivial, solving algorithms needed. Direct via stride formula, O1. Generators needed. 6 R L U D F B. 4 R U F L. Commutativity of generators. Generally no. Always, dimensions independent. Physical interpretation. Physical QB position. File address in storage hypercube. Section 10 discussion. Why the analogy is more than metaphor. The Rubik's Cube metaphor is tempting, but often superficial in applied mathematics. Here it is not. 3 structural features make the identification genuine. 1. Both are permutation groups on a finite labeled set. The Rubik group acts on 48 facelets, SBSA acts on H addresses. In both cases, a twist is a specific permutation, and sequences of twists are group words. 2. Both admit a solved state, serving as the identity. For the Rubik's Cube, this is each facelet in its home color. For SBSA, this is the identity element E equals 0, 0, WM, 0, corresponding to address 0. Every address is the image of this identity under some group element. 3. The stride formula is the Rubik group's commutator formula in the abelian case. In the Rubik group, commutators G, H equals GHG1H1 are used to move one QB without disturbing others. In SBSA, because the group is abelian, I, J equals E for all I, J. This is the algebraic reason SBSA dimensions are independent, and therefore O(1) lookups are guaranteed. The non-abelian nature of the Rubik group, which makes solving it hard, is precisely the feature absent from SBSA. The price of this simplification is that SBSA cannot represent the rich interdimensional correlations that a non-abelian storage structure might. The gain is perfect O(1) performance. Section 11 conclusion. We have established that the SBSA Hypercube is, precisely and not merely figuratively, a Rubik's Cube, an abelian one. Its 4 dimensions correspond to 4 face twist generators of an abelian group SBSA approximately equal to 4 times 2000001 times 1999981 times 10001, and every file address is recovered by a single application of the twist address isomorphism, Theorem 5.1. The God's number of the system is 4. Theorem 7.1, meaning any address is exactly 4-dimensional steps from any other. 3 properties make this formulation useful beyond the metaphor. The Coset structure, section 6, unifies point lookup and range query under a single algebraic operation. The stride formula, 5.3, makes dimensional sharding for distributed systems entirely explicit. Each processor owns a contiguous coset. The abelian property is not an accident of the implementation, but an algebraic certificate that O(1) performance is permanent and not coincidental. Future work includes the extension to non-abelian twist groups, where interdimensional dependencies exist and the Rubik problem of recovering an address becomes non-trivial, and the analysis of quotient structures arising when 2 dimensions are identified. References. Cattell, A. 2025.